Thanks, Regina. I'll just give it a minute just to let any final participants join us. I see the number is still going up, so we'll get started shortly. Okay, welcome everybody to another one of our EUMETSAT short courses. The topic of today's short course is Sentinel-6 Michael Freilich, which is an altimetry mission that we've been operating at EUMETSAT for some years now. It's still one of our newest missions though, so there's still lots to learn about it as the products have become available. So today, we're going to be joined by a couple of experts in both the mission itself and in how to access the data from it. And we'll share with you some insights into the mission and some different ways that you can start working with the data. But I'm just going to give you a bit of introduction first. My name is Hayley Evers-King. I work in the user support division here at EUMETSAT. I'm our marine applications expert. So if you contact our help desk, sometimes it's me you'll end up speaking to about our data, or if you've attended some of our training courses, maybe you've seen me there before. EUMETSAT, if you don't already know us well, is an international organization. We have 30 member states, and our main remit is to provide observations and data services for primarily weather, but also Earth system monitoring and forecasting and towards the climate services. In addition to this, we also have established further capabilities in partnership, particularly with the European Union and other satellite operators. This achieves synergy with the missions that we operate, but for the common benefit of both our member states and our wider partnerships. And this is where Sentinel-6 falls into this picture. If you're familiar with the Copernicus program, this is one of the missions that we operate underneath our sort of additional missions, if you like. And as a result of all this, we have strong international collaborations, both within Europe, with the US, again, particularly relevant in the case of Sentinel-6, with Africa, as well as with other countries around the world as well. Just to give you a quick overview of the different missions that we operate, you can see them all here, although this diagram, it seems every time I present it, is already out of date. Things are changing all the time very rapidly for us. You can see our mandatory programs there at the top, the ones that are providing most of our weather and climate data. And then there's been optional programs, which include the heritage instruments upon which the Sentinel-6 mission is built. So this is the JASON series of satellite ocean altimetry missions. And Sentinel-6 overlaps between this and our third-party programs, which are the missions that we run with the European Commission under Copernicus. So Sentinel-6 is a joint mission between those two kind of sets of programs, particularly as a collaboration long-term with the US and with our partners in France. In addition to the things you see on this diagram here, so we've got some missions that are coming up soon. You see Sentinel-4 and 5 there, more relevant for our colleagues who are interested in the atmosphere rather than the oceans. But we also have several of what were the high priority candidate missions under the Copernicus program that are now going to become future Sentinels that we will be operating, including CO2M, SIMA and Crystal. Of course, the latter has relevance for the altimetry community as well, and we hope we'll have another short course on that in the future as the mission comes online. So just speaking a little bit about Sentinel-6, I won't go through all the complexities in this diagram, but just to really make the point that it is an international partnership under Copernicus. There are elements of the mission from NASA, from NOAA, and then under European elements, that includes us, our colleagues at the European Space Agency, the European Commission through the funding of the Copernicus program, and our colleagues at CNES. So we all do different bits towards the mission. The mission is operated by us here at EUMETSAT. So in today's seminar, we'll have a presentation first from Vinka Roswaduk, who is an expert in satellite altimetry and also in training. So she's particularly well placed to give you this short course today. Vinka works with us. She's based at CLS, but she works with us here at EUMETSAT as part of our marine training activities. Her presentation and short practical demonstration will then be followed up by another presentation and discussion of some further resources for data access by my colleague Nicholas Jordan. Nicholas works in the user support division as well, and if you've been engaging with our new data services such as the data store and you've asked some questions from our help desk, probably Nick has been the person who's been helping you, so he'll be able to guide you through how this works in terms of data access for Sentinel-6 in that section of today's short course. For Q&A, please use Slido. If you've not used it before, you can just type into your browser, into your phone, sli.do, and then use the hashtag EUMETSAT33, and that will take you to the Slido for questions for today's short course. We'll deal with questions at the end, but feel free for any questions you have at all in there, and we'll try to answer them. After the course today, material will be uploaded onto the Moodle page where you registered through our training website. Of course, if you have further questions, our help desk is always open, so you can write to ops@eumetsat.int and they'll pass you on to the relevant expert to answer your questions. And if you're interested in further training, we run lots of different courses throughout the year, some longer ones, some more specific, some at different conferences you might be attending, and of course, an expanding short course series of which this is part. So please check out the training.eumetsat.in website for further information on that. And with that, I will hand over to Vinka to start with the first presentation. Thank you, Vinka.
Hi, I'm Vinka Rosmorduk. I'm working in Toulouse, and I've been working a lot with Altimetry for the Aviso Data Center for the basic radar altimetry toolbox also. And today I will show you what is new with Sentinel-6, Michael Freilich. The material I will show you are based from a number of contributors. So I'm the one presenting it, but a lot of people have contributed, in fact, in the background. So a few short words about the radar altimetry data uses. If you want more, you can have a look at the altimetry short course we did 2 years ago. So the kind of things that radar altimetry can see is a lot of surface 8, which can show eddies, strides, and meanders, and so help people forecast those in advance. All the variability in the ocean. You can also see very well the large-scale ocean atmosphere coupled phenomena like El Niño, La Niña, and forecast them, of course, also. You can also see other things than sea surface air height with the significant wave height and the wind speed modulus, which are derived from the altimetric measurements. You can see also things that are not over the oceans, such as water bodies level, lakes, rivers, provided the satellites goes over them. You can see also ice topography, also provided at least one satellite flies over them. And some other reflectors on the ocean, such as icebergs. And even in some places, you can study the solid land backscatter. And everything is open to your imagination for newer applications. One of the star application is, of course, a global mean sea level rise. And we've been monitoring the sea level from early 1993 now. So we are about to reach the 30-year period. And we can see the differences in geography about the trends of this sea level rise. Those are the most critical application because they need a very, very high level of accuracy. So if you have a question about this part, you can ask them through the Slido. So now, how we can reach sea surface 8 and significant wave height through a satellite. The simpler way of explaining it is this little scheme with the satellite, the water surface, and the reference ellipsoid, which is a mathematical approximation of the surface of the Earth. And then you've got the satellite, which is sending a radar wave towards the surface and back. Knowing the speed of the radar wave, which is the speed of light, you can deduce the distance between the satellite and the surface. And an important point is that you've got precise orbit determination instruments also on board, which enable you to compute the altitude. Knowing the altitude, the difference between the distance between the satellite and the surface, you can deduce the surface height. A slightly more realistic way of seeing it is that the wave is not exactly the speed of light in the void because you've got the atmosphere. So you have to apply a number of corrections. You've got water in the troposphere, which is slowing the wave, electron in the ionosphere also. You've got dry gases in the atmosphere. You've got also things that are impacting the surface, such as atmospheric pressure. When you've got big anticyclones, the sea surface height is lower than when you've got a depression. You've got also the fact that the wave crests reflect the radar less than the trough because they are smaller, in fact. And of course, you've got the tide. All the corrections are provided within the level 2 data, and they're subtracted from the raw sea surface height. Well, this is for you to understand what's in the data that EUMETSAT is distributing, and that you can find in the notebooks that are in the GitLab. We will show you later on. So now we've got the satellites surrounding the Earth, and this is giving you something like what you're just seeing here. This is a little animation to stress a point. I prefer to make clearly that the mesh of data you add is the real altimetry measurement, not the nice filled up map you are seeing just now. So my point is altimetry is not imagery for now. I won't say that in a little more than 2 months now, but for now and for Sentinel-6, you've got a narrow thread of measurement just beneath the satellite. That's what we call a long track data. You don't have natively an image. And for Sentinel-6, you've got a map such as the ones on the Google Maps right, sorry. And left, you've got a little animation which is close to the video I showed earlier. It's to explain you the way the mesh of data is built. So now a little higher level of complexity. In practice, where there's not a little chronometer on board the satellite measuring the time it goes for the radar wave to go back and forth. In fact, the computation of the time is done using the radar echoes, or an average of the radar echoes that is called the waveforms. So the waveforms are built somehow like this. So you see here, through time, 4 steps in time with the satellite sending the wave. Sorry, I will use a pointer. No, yeah, I can have a pointer. Satellite sending the wave towards the surface. Here you don't have anything arriving on the surface. Here you've got a little on the surface, then it's rising. and decreasing a little bit. This is what we call a waveform. This is a classical altimetry waveform for a calm sea. So the range, the satellite to surface distance, is built using this information. And here you see another animation thanks to ESA with low resolution mode. Oops. Oh, sorry, I will go back to not a pointer because I can't control the animation. So you see here you see the satellite, the measurement, the waveform measured, and if you see here, you've got the side view of the surface and the top view of the surface. So you've got a number of different views that the wave is bouncing back the surface and illuminating part of it. And then you've got the waveform built from that. This is what is called the Brown model of a theoretical waveforms with a number of parameters extracted from it. So you've got the midpoint of the leading edge, the edge mounting from the increase of power when the radar wave touch the ocean. And the midpoint gives you the time, and the time gives you the distance. You've got also the backscatter coefficient, which is computed from the power reflected. You've got thermal noise, which is a starting level. And the slope of the leading edge is giving you the significant wave height, while the trailing edge slope is more the antenna midpointing, because you're supposed to have a real nadir straight towards the surface pointing, and sometimes it's a few tenths of a degree off. So to explain about the significant wave height, you've got here the same scheme than before, but right, you've got the case of rough sea. And you see that in case of a rough sea, the echo is slightly distorted because the waves is bouncing on the crests of the waves first, then on the troughs, then a little, and stay on the troughs. So the waveform is more spread over the time back. So this is a way of measuring sea surface height from a satellite. And here a small animation showing how those parameters can change depending on the distance, the significant wave height, and the wind speed. Also, the wind speed changes the roughness, so the power which is back straight to the satellite. Or if you've got questions, there's still the slide. Oh. So now a few words about specificity of Sentinel-6 Michael Freilich, because what I've explained just before is true for any and every altimeter. So altimetry began as early as the 70s with test bed with GEOS3 and Skylab. CSAT was the real first altimeter flying, but sadly it only lasted 3 months. The GeoSat was classified but had interesting in measurements. And then in the 80s, NASA and CNES had both plans for missions, And they decided to merge them into a satellite which was called TOPEX from the US altimeter, Poseidon from the French altimeter, which was launched 30 years ago, a little more than 30 years ago, on the 10th of August 1992. And in the meantime, ESA launched ES1 with also an altimeter, among other sensors. TOPEX Poseidon follow-on was JSON1, launched in 2001, with only the Poseidon 2 altimeter on board, plus the precise orbit determination and a radiometer. Then JSON2 and 3, with EUMETSAT and NOAA joining from JSON2. Then from JSON3, Sentinel-6 took over with phases where they were following each other closely. So this is not JSON3 and Sentinel-6. This is TOPEX Poseidon and JSON1, but the principle is the same. Both satellites are following each other so that we are sure that they're measuring nearly the same thing, so that we can calibrate the one over the other. The other in situ calibration, statistical calibration of the mission, which is true for any Earth observation satellites. In fact, in the case of Sentinel-6, Michael Freilich and JSON-3, there was more than 6 months of calibration phase because the agencies decided to also intercalibrate the redundant altimeter on board. In fact, you've got 2 altimeter on board such satellites in case one when goes off or has problems, so we can switch on the redundant altimeter. It only happened once, as far as I know, on TOPEX Poseidon. So my Sentinel-6 Michael Freilich was declared fit for duty in March 2022 after being launched in November 2020. Why I'm talking so much about TOPEX Poseidon JSON, it's because with Sentinel-6 now joining, it's what we call the reference mission. It's a mission which has the highest accuracy, the stable orbit to serve as reference for the mean sea level variation measurements, since, as I mentioned earlier, it's one of the more demanding applications of altimetry. So now Sentinel-6 Michael Freilich is the reference mission for altimetry and sea level. So it is an altimetry dedicated mission on a non-synchronous orbit, which means it's not in phase with the sun, but mostly the point is not with tides. It was launched on the 21st of November 2020 to take over JSON-3 for at least 5 years and a half, providing thus a continuous intercalibrated measurement series on this orbit since October 92. So we are nearly at the 20-year climatology period. A Sentinel-6B, which will be a copy from Sentinel-6A or Michael Freilich, will be launched in November 2025. And just as, I forgot to mention that you may find the name JSON CSA instead of Sentinel-6A. It's to mark the continuity with the JSON series, but it's the same anomaly satellite, which was launched and left its rocket as in this movie of NASA. So on board you find an altimeter, well, 2 altimeter in fact, because you've got a redundant one, which is descending from the Poseidon one on board Topex Poseidon and the different Poseidon version on board the different JSONs. It has also improvement made through Thrall on board Sentinel-3, but in fact the manufacturer is the same. So it's evolution from the Poseidon on board Sentinel-3 and 6, and a similar complement of a radiometer, which is a JPL instrument, and 3 precise independent orbit determination instruments. You've got a laser reflector. From station on Earth, you're sending lasers towards the satellite to measure precisely the distance. You've got a Doris antenna from station on Earth, sending a radar wave measuring the Doppler shift. And you've got a GNSS instrument also computing the distance from the different GPS satellites. So in the years to come, for the Copernicus program, you've got all those missions which are or will be controlled, processed, and distributed by EUMETSAT. So I mentioned JSON 2, JSON 3, Sentinel-6A and B. You've got currently also Sentinel-3A and B. The Sentinel-3C and D are planned. There's also a Crystal, which is planned, which will be more a polar observing satellite. And the follow-on from Sentinel-3 topography mission and follow-on of Sentinel-6B is under study. So, but it's planned. There will be a follow-on from Sentinel-6B. So what's better in my Sentinel-6 Michael Freilich than from other satellites, Altimetry satellite? So on Sentinel-6, you've got a SAR mode, which is also called a delayed Doppler altimeter. In fact, the radar wave is emitting pulses at a much higher rate than previous classical altimeter. But what the point is also that the frequency received is used to compute the direction of the beam using the Doppler effect. And all in all, you've got a coherence of the signal sent for about 2.5 seconds. The Doppler shift use enabled to split the radar footprint in kind of slices across along the track, instead of having a round footprint, such as in classical altimeter. You've got kind of slices of this round footprint, providing thus a better along track resolution, or a better quality of the data at higher resolution, in fact. So a little animation. Here you see you've got Doppler shift difference if the radar wave is bouncing in front of or behind the satellite, and using the little change in frequency, you can use this to average the different slices coming from different direction at a given point. So yeah, it's the same plot, same scheme than the beginning, but for the SAR waveforms. So you see here you've got same kind of plot with the satellite in profile, the surface, and the waveform below. And you see that your slice of the beam is leading to much peakier waveforms. The same in animation, comparing low resolution and high resolution modes. Oops. So one of with those a number of animation of the same slice of the footprint, which are also called the stack data average, lead to a lower noise and more accurate range, including using the finer long track spatial resolution provided. You'll find them in the 20 Earth data. You've got also less ambiguity about what surface is observed, even when you're close to land. So you can go closer to the coast, even if really on the few centimeters of water close to the beach, and it's still a mix of land and water that your altimeter will see. So the Sentinel-6 is in high resolution mode, meaning the SAR mode, over most Earth up to the 66 degrees north and south, due to its orbit. So it's seeing ocean, a little ice, not the polar caps, and land waters. About the precision of the things, here are a few figures. You've got the observed, what is seen from the data we've seen from the past 1 year and a half, nearly 2 years. The requirement, the figure which was decided as needed for the missions, the goal which are the figure hoped for, and last you've got the JSON-3 low resolution only satellite. So you see you are not yet exactly to the goal, but we are better than the requirement in the observed either the noise or the RMS. Even in non-time critical, which is a long period, the best quality but long period data, the short time critical, which are the data provided 2 days after the measurements, and the near real time, which are in 2 hours, those are the less good data, because in part of the orbit, you need time to compute the best orbit possible. So we are very close to the hoped for quality, and a few improvement will should enable to reach them very soon. So with those capability, with the SAR mode, the current development is fully focused SAR. The idea is to process the synthetic apparatus using the longest possible integration time. I've said earlier that the radar waves stay coherent for 2.5 seconds, and if we use all those 2.5 second view of a given slice of data, we can reach something like 50 centimeters of resolution along the track. This is not in the current processing of data. This is current ongoing researches, but we can hope it will come into the operational or standard product one of these days, even if maybe not in real time, because it's time-consuming processing. So it's especially interesting for coastal, for swell wave spectra, for small water bodies, rivers, etc. Maybe less in the open ocean, but maybe as new users, you can find a new application of this capability. So this is a little scheme to explain the differences between the different modes. So the conventional altimetry, as discussed earlier, you measure all over a disk of data. The phase is not exploited, so delay Doppler, the Doppler shift. The unfocused SAR, you compute by burst of 64 emission. This is the current mode, standard mode, SAR mode on Sentinel-3 and on Sentinel-6, and also Cryosat-2. In fact, it's the pioneer mission is Cryosat-2. Summing the different independent looks, we can reach noise level reduction. Now, if we use a longer time of integration, we can reach a higher resolution along the track, which is possible with Sentinel-6. Sentinel-3 has a few ghost detection because of a different scheme of emission reception, both with specific processing. And you see, if you're interested, you've got the reference given in the slide. And over river, you can have things like that. So you see for Sentinel-3, unfocused SAR, focused SAR, radar over the Garonne River, close to here in Toulouse. And the Sentinel-6, unfocused SAR and fully focused SAR. So you see, you can have much more details over the Garonne River flow. Again, if you've got questions, you can ask them through the Slido. And just a few words about the data products. So the data products are named and ordered through a level of processing. So you've got the level 1A with individual echoes, instrumental calibration applied. From this, you can do the fully focused SAR processing. The level 1B include the calibrated waveforms to be combined with level 2 to form the equivalent of JSON's sensor geophysical data record. The level 2 are equivalent to what was geophysical data record for the JSON. There's a new NetCDF format we're using groups, and they are provided also in reduced format with only the main interesting parameters or variable, and also in near real time in buffer format for meteorological application. The level 2 plus are reduced with computed corrected heights, only essential variable for sea level anomalies, significant height and wind, and the validation flags too. And the level 3 are harmonized with other missions, and they're also distributed by Copernicus Marine Service. All those data are distributed by EUMETSAT for Sentinel-6. So just a few tries of explaining with more concrete phenomena, the level of data. The level 0, you mostly will never see them. It's the things that the space agencies are receiving from the satellites. tried comparisons with cooking with tagliatelle al ragu. So the equivalent, I propose that you grow your wheat, your cow, pork, tomatoes, carrots, then you cook. The level 1, you explore new processing. These two main to explore new processing, new parameters, test over other surfaces. Equivalent, I'm proposing, is to make your pasta from flour you will have bought. You grow your vegetable and you wash, peel, and mince them. The level 2, you will buy your meat, tomato, vegetables, and you cook. You buy the pasta and you cook them too. The level 3, you buy the sauce, the pasta. You add something of your own, like a pinch of thyme and some more meat or salt, and you let it cook. The level 4, which are the grids currently distributed by Copernicus Marine and Service and Copernicus Climate Change Service. You buy everything from next door Italian takeaway restaurants. And the visualization tools outputs, well, you take a photo. So that's try to explain with a concrete comparison what the level of data are and what you can do with a different level of data, provided you feel like cooking your own data. So this is short differences between JSON3 and Sentinel-6, the different latencies. What I wanted to stress here is got near real time in 3 or even 2 hours, the short time critical in 2 days or even less for Sentinel-6, and the non-time critical, you've got a 2 months latency because you want a better possible orbit, mainly. So if you need very high precision and you're not in a hurry, prefer the non-time critical. The short time critical, if you can wait for 2 days or so, and the near real time are mostly used for wind and wave from the operational meteorological agencies. And for the non-time critical, the idea is to have them as homogeneous as possible, so you've got regular reprocessing of the whole series, and the idea is to try to have the complete series from topics within homogeneous in the end at some point. So format novelties, we've got a grouping and different variable naming than in previous altimeters. You've got separate high resolution, meaning the SAR mode data, and low resolution classical mode data products. The waveforms are not anymore in level 2 data like in Sentinel-3, but in level 1B. The file names are different depending on the track, the alpha orbit, and you've got also a separate radiometer product. For the group, this is a little scheme to show you that you've got global attribute depending on applying on all the data. You've got the data at 1 Hertz, data at 20 Hertz, that's the higher resolution. And you've got the 2 different frequencies provided by the altimeter, KU band and C band. Only KU for the data in 20 Hertz. And then you've got a variable for each. So the file format is more sorted. You don't have nearly 200 variables in a row. You've got different groups to find them more easily. You've got also improvement on the reference mission with the interleaved mode, which is a radio emission reception pattern, which allow low resolution, high resolution modes simultaneously, thus ensuring the continuity with the previous mission and opening the door also to comparison and research on the two modes. The 1 Hz range noise, as I showed earlier, is below 1 centimeter. We are talking of a satellite which is 1,336 kilometers above our head. And we managed to have noise below 1 centimeter. We'll have short-term critical data faster than JSON. All the data are provided, produced, and distributed by EUMETSAT. And as take-home messages, I would like to stress that with Sentinel-6 Michael Freilich, you've got both changes and continuity. The mission is benefiting from the unremitting work on accuracy for the past 30 years. It is enabling a seamless transition between JSON 3 and Sentinel-6. And you've got also improvement on the data accuracy, new capability, and new possibility to be explored. The format is close to the last JSON 3 formats, and reprocessing is ongoing for the older mission so that you will have as homogeneous as possible series. And the story continues with Sentinel-B to be launched in 3 years. So if you've got questions, there's still the Slido to ask them. We'll answer them in the end. And now I will switch to a notebook. We've got prepared a notebook with Sentinel-6 waveforms in a coastal area. So I will show you for two different modes possible for Sentinel-6, the difference in the waveform in coastal areas. For this, the first thing will be to download the data, and then we will compare both modes in two cases. So those notebooks are available on EUMETSAT GitLab, and we will provide you with the address later on. So the notebook is Python. You've got first cell, you define the different different library you need. Here we define some function we will need later on. Especially, we will need the angle of the track with respect to the Earth. And in fact, I can show you what is this track. This is the track, the Alpha Orbit 70, which is going through Brittany, the Bay of Biscay, coastal Bay of Biscay, crossing France, Mediterranean, crossing Algeria. So I need the angle to be computed, and we will define the product directory. And some parameters. So I'll put the download data to true so that you can see it's quite easy and fast to download. Well, got only 2 files. I've defined in advance the track direction, but you can compute or find it in the level 2 data. And I've got 2 test cases, one for a place called Fort Boyard in coastal France, and the other is in Algeria, in the port city of Taher, which is shown here on Google Map. Few parameters for the plots. And here it's the data acquisition from the EUMETSAT data store. So we will find the data in 2 different collections because I want a low resolution collection, level 1B, and the high resolution equivalent product. So those are the file names. When you know how to read them, you've got the name of the satellite, you've got the name of the altimeter, the level, the mode, the beginning of the alphabet, the end of the alphabet, the time of the processing, the cycle number. Here it's a cycle 52, the number of the alphabet and the number of the orbit. And F06 is the reprocessing version. So to access the Sentinel data, we need a Python module, dedicated Python module. You've got also credentials. I've programmed mine, but I won't give them mine to you. Sorry. But you can quite easily register to the EUMETSAT user desk to have an access, and then it's quite easy to do. And with that, you can have a token which enable you to access the product. Here you've got a download of the first one and unzipping. The part of the code is unzipping. And the second one is a bit bigger, so it will take a little more time. But in fact, I've got already done. So for my use case, for my case studies, I will use part of the file name to deduce if I'm in low or high resolution. I'm picking it in the product ID so that I will use the information later on. Since the data are ordered in groups, you have to read each group as it was a separate data set. So here I will use data from the main group and from a subgroup, which is data 20KU. I will use sample for the waveform and subtract on a region, which I defined earlier around my point of interest. I'll subset all the coordinate and waveform variable. I need the latitude, the longitude, the time, and the waveform power. I'll use my function for the angle defined earlier and regrid the sample and time. And I want to do something that is not completely meant for. It's to plot the waveform in color with respect to its geographical context. So I will compute an x and a y with respect to the longitude and the latitude to plot the waveforms. Just to show you where we are. Here you see we have I've subtracted only the little blue line here. So for the low resolution mode, if I plot the waveform, you see something like this. So this is a sample from 0 to 255, and the ordinate is time. So the track is a descending track, so you'll have time ordered top to bottom. This is a useful plot because, in fact, the parabolas are off nadir echoes. See that the radar wave is not always reflecting just beneath the satellite, but sometimes off nadir because you've got a small reflector or small lake or a cliff or something, which are reflecting the radar, but not from what it is expected to come from. If I plot that on a longitude and latitude, got something like this. Note that this is not a real representation of the geographical width of the radar beam. This is purely to see the thing with respect to the coast. So if I'm plotting that with respect to the coast, this is the track crossing the coast at the red square. And you can see here you've got a marked difference between what you see here and what you see when you've crossed the coast. Now we will do the same, but with the high resolution. So you see here you've got quite different things. For one, you've got 512 samples for some of the high resolution data, not for that one. For that one, the last half is put to 0, in fact. And it's quite different, and you would see much less parabolas in the data. If you compute now on a geographical context, you see you've got quite marked difference also, but more straight to the coast. The data are not linking onto the land. So here you've got both cases, high resolution samples and the low resolution. Here you see you've got parasitic reflection, but much less than in the case of the low resolution one. So now I will show another cases, which is a little fun one. I won't upload the data because it's the same track. This is a case of Fort Boyard. I don't know if you know Fort Boyard. Fort Boyard is in the coastal waters of France. It's a little fort amid the water, completely in the middle of the water. It's something like 30 meter high on maybe 100 meter long, something. So if you look at the same values, I'll skip the data download part. I extract my data. I'm again plotting the area where I am. So you see here we are near the Garonne River mouth, a bit north of it, in fact. The low resolution plot, to see a lot of those parabola, meaning that you've got a lot of different reflector in the area. It's a very complex area for altimetry. In low resolution and on a map. So you see here you've got the Orléans Island, the X Island here, and the square is the fort in the middle of the water. If I look at it in high resolution, this is a rendering is quite different, and in a geographical context, see here around the fort you see different leading edge. The higher value of the waveform marks the leading edge of the waveform. And if we compare side by side, you see here you've got different leading edge, different peaks here, and here you see a shift in those. Now I will have a look in 3 dimension, and I'm not sure you will see it on your screen, but at the beginning, in the noise of the waveform, before the leading edge, before the steep rise, you will see small peaks in the waveform around here and here. And if we look at this on curves, which is less showy, but maybe easier to interpret, yeah, it's a single waveform. I have selected about 10 waveforms, 5 before, 5 after the one crossing the Fort Boyard place. We've cut the waveform because we are mostly interested in what's happening at the beginning in the low nose. So this is the top of the waveform, and this is only the beginning of the waveform, and this is where I want to focus on. So you see this little peak and different little peaks. And those are, in fact, the wave of the radar bouncing on the fort top before it comes to the largest part of the ocean. So this is more or less fun case, but this is one of the way to detect an iceberg, in fact. And the advantage of the Fort Boyard is that it doesn't move around, so you're sure to find it at the same place. It can be different depending on the tide. Here the tide is not at its lowest, it's mid-tide about, not a very high neap or low tide, but about mid-tide. So but because in very low tide, you're not sure you won't be looking at wet sands rather than water. So those are ways to find different things than Sisyphus 8 in the data. And you can see the differences between the resolutions provided and the things you can interpret in them. So maybe it can be interesting to look at those shifted leading edge, or maybe so the repeated peaks here. It's a field of research to interpret those reflections, those echoes for new applications, and this is why we are opening the door to new things and welcome you to test and try other things. So Niklas, I'm leaving you the floor.
Perfect. Thank you very much, Winka. That was very interesting. I will take over now to the data access part. So I will show you now how to access the data Winka spoke about in the last couple of minutes. So how to accessing the Sentinel-6 products. There are several ways. So when you are interested in the operational products, then we have two ways at the moment. The first one is the SFTP server. Maybe some of you already knows about it. The SFTP server gives you a 7-day rolling archive of all the operational data. The missing point there is that it's just an usual SFTP server, as you already know, maybe. So you have no filtering options for the area of interest or for time search or orbital parameters, but we have the data center. And the data center is an offline ordering. That means that you don't have the data on demand, so you can't go there and just downloading the data. You are ordering the data you need. You can say in the time search, and you can say which area of interest you have, and you can also define which output data format you need. So if you need native data or maybe as a geotiff or whatever, so you can all configuring those things there. But then you have to send the order to us, and the data center operators on our side are packaging your order and getting all the data together you need, and then send you a link to an FTP where you can download your data, or you can also decide to get a hard drive with the data through post or whatever. You can decide several things there. But this means because we have to packaging all those kind of data and transforming these in the data you need and all this kind of stuff, that you have to wait for the data, and this is depending very much on the amount of data you need. So it can take several hours, but it also can take several weeks until you get the data. So we decided to get all the operational data also into the data store. The data store is our new data access service we want to go with you in the future. So the data store is an on-demand data store, how the name says. So you can search there for a specific time, for area of interest, for orbital parameters. So that's very nice. You can use it through a graphical user interface through the browser. You don't have to install anything, or you can use APIs or our data access client. I will show you in a minute. So at the moment, we just have there the reprocessing data, as you can see on the slide. I'm not sure if you can see my mouse on your screen. So yeah, you can see it.
Yeah.
Perfect. So as you can see, we have at the moment just the reprocessed data there. But also this, you can search by time and area of interest and all this kind of things. But we are working very hardly to give you the full operational product palette in early 2023. So the plan currently is to have all the Sentinel-6 data in Q1 next year in the data store. And this will give you a huge opportunity to search easily for the data and for the full spectrum of data, and not just a 7-day rolling archive, for example, or ordering the data and waiting until we've sent you the data. So let me show how the data store works. I went already there. So you can reach the data store through our URL data.eumetsat.int, and then you will see this page. And it's a whole catalog of many collections we already have in there. So for example, you can just search for altimetry data, and you can find a lot of different collections and data sets. And now we have the advanced search here on the right, on the left, sorry, where you can say you just want to have data from the Sentinel-6 mission. So, and now we've got 6 results. Maybe I've got a bit more than you when you try out, because I have some more internal collections here there, but it doesn't matter for you. So you can see all the collections we have in this case. And now let's say we want to access these data collection. And now you will get into the data browser where you can search for the data and for the specific products. So as you can see here, we decided to use this collection. You can see which time range for this data is available. In this case, from December 2020 to April 22. You can search for, in this time range, you can search for a specific day or a week you want to have the data for. You can use the file name search to find a very specific file. If you know the file name and you want to have exactly this file, you can use the file name search. You can sort by sending time or whatever. And of course, you can use it to search for the orbital parameters like orbit number, relative orbit, cycle number, and also the area of interest. When the operational data are arriving in the data store, you have also the opportunity to search for the timeliness and some other aspects. But for example, let's say we want to search for data on the coast of France, then you can just say, give me the area of interest, a rectangle, for example, or you can also use a polygon and say show results. And then we will get just the data from this specific area of interest perfectly. So we didn't get any data for this time range now. So I opened the time window a bit, and now we get a lot of data. You can see here 99 products were found, and this is the list of products. And when you click on the products, you will see the overlay, the footprint of this product. You can get more information about the specific product by clicking to this little button, and you can see what is included in this data set. So you have the metadata and the manifest file and the measurements itself. You can have some more information about it. This is very cool. And now, and this is the biggest point comparing with the data center, for example, that you can just click on this little download icon, and as you can see here at the bottom, the download starts immediately. And when you need more data, for example, or all the data, you can just select it and add it to the cart, and now you have it in your cart and can download the full data set. The cart doesn't mean that you will be charged like on e-commerce cards or whatever. It's just means it's your space where you can put all your products you want, so you can download it all at once and not every single product. So this is very cool and a very nice place to investigate our data, not only Sentinel-3, Sentinel-6 data, also other collections we have there, and you can just click through the data. You don't have to install anything or configuring anything on your local machine. Another way to access our data store is through the data store API. And here we are recommending much to use EUMDAC. It's a little tool. It's our EUMETSAT data access client. So it comes as a Python library or also as a command line interface. So when you want to have the data programmatically, I highly recommend you to use EUMDAC, because we take a lot of work from you, so you can focusing on which data you want and downloading and all the stuff and behind of it, like sending requests to the API and all this kind of things we are taking care about. So EUMDAC is completely free of charge. You can download it through Conda, or also when you use more likely PyPy, for example, you can also install the Python library through PyPy. It supports more or less all of the features, also the graphical user interfaces phase of the data store provides. But it gives you a bit more flexibility because you can use code and configuring all of this kind of stuff. So you have more flexibility on using these different filtering parameters, for example. So you can filter the Sentinel-6 data for relative orbit number, absolute orbit number, cycle number, everything you can see here, but also for relative path number and absolute path number by using a little bit of code. We have it here as an example. So the cycle number, for example, is included in the metadata and as a search parameter. So you can just say cycle equal 5, and you will just get the products from this cycle. Or if you want to get the relative path number, you can use the file name search I showed you before in the graphical user interface, and use this little asterisk here to just cut out a specific part of the file name, and now you will get all the files that has included this this string. So that is quite easy to use, and as you can see here, you can also calculate some parameters from it to get these kind of data for specific absolute path number, for example. It looks maybe a bit complicated, but I will show you in a minute. We will provide you a notebook, a Jupyter notebook, where we use this formulas to get the products for absolute path number. So you don't have to do it on your own. You can just copy and paste it from our code. So let's go back to the browser. I opened here a notebook because we are a bit of tight in time. I pre-rendered it also, but you can find the same, exactly the same notebook as I have here, also in the repository Haley shared in the chat. So this notebook is especially for getting data from the data store using the EUMETSAT data access client, or in short, EUMDAC. We have also a notebook about getting data programmatically from the SFTP server. You can find it in the repository too. So we can't go through it in detail, but I will show you the most interesting parts. So as Winke already showed you, you need credentials to use EUMDAC and connecting with the data store. You need the credentials to authorizing and get all the possible products. Otherwise, you are just able to search for data but not download data. And these credentials are quite easy to get. If you have an EO portal account, you can log in the data store here. When you are not logged in here, you can find the login button. In my case, I'm already authorized with the data store. And when you click now on your name here on the top, you can see here a little link to the API key page. And this brings you to this page. And here you can find the consumer key and the consumer secret you need to authorize with EUMETSAT to our services. So it's quite easy to get. And when you have it, you can just save it here in such a file or paste it directly into the notebook. But please be aware that you shouldn't share this credentials with any other users. So I already have this in my JSON file here, so we can go through it. We decided to use this specific collection, the Sentinel-6 level 2 LR reprocessed one. And now we can, searching in this collection, we can say we want to have the full name of the collection, for example. And here you can see the very cool thing is on EUMETSAT that you are not, you don't have to care about the requests or whatever. You can work with objects, and objects means the collection we decided to use is now an object, and this object has different variables you can just call. And in this case, we just said for our selected collections, we want to get the title. And here we are, this title is printed. So you don't have to send a special request to get the title and special request to get the description or the available time range. We have all this included in the objects, and you can use it as you want. Same for this one, we can print all the possible search options we have for this collections. Different collections have different opportunities to search and filter for the data. And here you have a lot of search options to find the data you need, as you can see. So let's go a bit deeper into an example on how to filtering by time, for example. First, we want to show you how to get just the latest product in this collection. And this is quite easy. We just say in the selected collection, we want to search, and then just give me the first product. The first product is always the latest, and we will print it. And now here is the product name we have as latest in our collection. But when we want to look for a specific time window and just get the data of the specific time window, we can say through a datetime object from the 23rd of January from this year, between 4 p.m. and 4:15, we want to get the data. And here we are. We just got these two products that are from the defined time window. So it's quite easy, as you can see. You can also search for a specific area of interest, as you can see here. Here we are just defined our area of interest. In this example, we used a well-known text format. With this format, you can use search for cycles or circles, or for polygons or rectangles or whatever you want. A very artful polygons you can create are used in this format. But if you're more likely to use the bounding box format, you can also use this format with EUMETSAT. So you can decide which format you want to use, and then search for data specific for this geometry we defined here. And now we will get back the product itself. And also the product is just an object. It's not just a string. We just see here the product name, but behind this name, there is an object included. So you can search in the product, for example, and get just a specific file. And here we have an example on how to just download the XFDU manifest XML file, for example, or you can also filtering for orbital parameters, as I showed you in the presentation before. We have here different examples, filtering for cycle or relative orbit, and you can also combine all these different parameters. So you don't have to use one by one, you can combine all the parameters so that the intersection of all these parameters gives you exactly the product you need. Here you can see the searching by file name to get all the product that have a specific part in the file name. In this case, it's 035_UM, for example, to find products from a relative path number. But as we told you before, you can also filter for a specific cycle number or a relative path number by a bit of calculation. And the formulas you just saw in the presentation before, we have here also in the Jupyter Notebook, so you can just copy it and paste it into your code or just play around with it from this notebook. So you don't have to translate it in your own code. You can just use the one we provided here. And here you can see how this works then for downloading products. So this is a very comprehensive guide on how to download Sentinel-6 data from the data store. It's quite easy, I guess, but if you have any trouble, we have also some resources to check out. And let me show, before I hand over back to Haley, let me show how you can find more information and help from our side for your needs. So when you are on our website, EUMETSAT.int, you can go to the satellites menu option, and then we have this little page, how to access our data. I said little page, but in reality, there is a lot of content behind the page. And when we scroll down a bit, you get a guide for new users to start. You get links to EUMETView and our other data access services, like also the data store. And you will find this very big picture with the text data access service knowledge base. And this is our knowledge base with a lot of documentations around our data access services, but also, for example, mission-related knowledge bases like for the Sentinel-6 mission. But let's go to the to the data store knowledge base. And in the data store knowledge base, you will find a lot of information on how to use the graphical user interface, for example, but also how to use the APIs. Yeah, a lot of examples on how to find specific products to get the products you need. And what you get here also is the contact to our help desk. And if you have any questions, you can, of course, ask them now in our Q&A. But if you have in the next days questions, or whenever time you need us, you can just write an email to the ops@eumetsat.int to our very nice help desk people, and they will find the perfect person to help you with your needs and to answer all your questions or find a solution for the issues you may have. So you can reach us out at any time, and we are very, very happy to help you. That's our job, and yeah. So, and what you can find here also is the EUMETSAT Data Access Client knowledge base I showed you before. It's a bit small and a bit more comprehensive and focused on using the Python library and the command line interface. And here you can find more information on how to install the EUMDAC, the client, or you can find more information on discovering collections, filtering products, and all this kind of stuff I showed you already before. And you can find also some more information, and maybe that is also something interesting, something that is interesting for you, how to use the command line interface. So we are providing also binaries, so when you don't have the access or permissions on your local machine to install anything, you can just download the standalone binaries. You don't have to install anything. and you can use the command line interface as the same as you would do when you install it. So, and you can search for collection and download products and all this kind of stuff there too. So before I finish, let me show you some last slides. I showed you how to access the knowledge base. I very recommend you to have a look into the knowledge base. There are a lot of examples. If you need an account to access the data store and get your credentials to using it with EUMDAC, you can go to this URL, eoportal.eumetsat.in, to register for an account. It's completely free of charge, so you are very welcome to do so. Here's also the email address. You can reach out our help desk, and some more links to our training pages and the notebooks we showed you before. So the presentations will also be shared with you afterwards, so you can find all the materials we showed before also afterwards to try it on your own. Okay, thanks. That was it from my side, and now I would hand over to Haley again.
Okay, thank you very much, Nick, and thanks very much, Vinka, for those great presentations. I learned something new today as well, so this is really good. We've had some questions come in, so Regina, can you share the Slido for me? And we can see what the questions are. Okay, thank you very much.
You can start from the bottom.
We'll start from wherever you like. It's fine. Yep. Okay, we can start from the top there, I think. So, question here from Luigi: why is it relevant that a small along track resolution, e.g. 50 centimeters rather than 10 meters, if what matters is the height of the sea surface? So, Vinka, would you like to have a go at answering this one? Oh, you're muted, Vinka. So.
For the open ocean, I'd say it probably doesn't matter. When you're looking at small bodies of water over land, if you're looking at coastal areas, having a sea surface height every 50 centimeters or so would be interesting. In the middle of the Atlantic Ocean, probably not, indeed.
I would agree with you on that one. Okay, and then the next one is, in which way can a satellite altimeter be used to monitor events like El Nino and La Nina? Is the altimeter used in conjunction with other sensors, e.g. sea surface temperature? Yes, so I can answer this a little bit, but Vinka, maybe you can comment too. Satellite altimeter is able to be used as a kind of proxy for looking at the changes relating particularly to the heat content storage in El Nino and La Nina conditions. But of course, this is a multi kind of impact phenomenon. So it works very nicely to use the data in conjunction with other data sets as well, particularly the sea surface temperature, but also things like the ocean color, which can be useful for the impacts as well. So Sentinel-3 is a nice instrument in this regard, but so is a lot of the downstream data sets that are produced by it. Vinka, do you want to comment on anything else with regards to altimetry?
Well, yes, indeed. You can see El Nino, for example, as a big, higher than usual sea surface height area, bigger than South America, going from Indonesia to South America. So you can see it in the data about 2 months in advance. So it can be useful because it's reflecting, as Haley say, everything that is happening in all the water column, including things that are underwater and then sea surface temperature might not see as well.
Yeah.
But of course, the real studies are not anymore using one single sensor. Most studies today are using as many sensors as available and possible.
Yeah, I think that's a common theme in applications for satellite data these days. The more data you have, the better you can resolve all the different parameters that are changing in different phenomena. It's a great question. Next one is, which is the ellipsoid used to determine the height of the sea surface? Does it take into account the topography of the bottom of the sea? Now, I have an idea, but I'm going to ask Vinka to answer that one. Mhm.
The ellipsoid is a mathematical surface. It's really an ellipsoid. So it's approximately at the water surface, but it's purely a spheroid. It's not taking the topography of the bottom. In fact, some altimetry measurement can help in deciding what's happening in the bottom, because the surface, the real surface, not the ellipsoid, the real surface observed of the ocean is reflecting differences in gravity. So if you've got a big, heavy mountain under the sea, you should have a small bump over it on the ocean. But it's not that easy to do the inversion. So you can do topography, bottom topography, but mostly mixing altimetry and in situ measurements.
Okay, thank you.
But the ellipsoid is purely mathematical.
Regina, if you can scroll for me. Okay, yep, and we've got what statistical technique is used to determine a 3.53 millimeter per year sea level rise with a sea level measure resolution of 0.62 centimeters? Is that 6.2 millimeters error?
And Laurent, yes, I will. And if you ask me, I can.
At the top question, yes, they will. We'll share all the content on the middle page.
Yeah. It's just well, averaging is lowering the noise for one. So it's well, so 0.5 centimeter is noise, instantaneous noise. Here we are averaging over a full cycles of data, the sea surface 8. So we are removing noise by averaging, in fact.
Okay, thank you, Vinka. Are there any more questions? You can pop them in the Slido. We still have a little bit of time, I think.
Oh, I thought I've
You've explained everything so
everybody
well,
in
Vinka.
details.
Yeah, in response to the top question, as Vinka said, we will put the material online. It'll be on the Moodle page where you registered for the course, training.eumetsat.int. So we'll put both the presentations up there, as well as the links to the notebooks, which I'd encourage you to go and run. You're very welcome to reuse any of this material as you would like. We offer it openly for your own purposes, sharing with your colleagues, teaching or training under your own jobs. But if you do use it, we'd love to hear about how you're using it. It's nice for us to see the impacts that the work has. So please do keep in touch. And if you'd like to collaborate on anything with regards to those training events and things, you can just let us know. This will have, oh, sorry, Vinky,
for the animation, I must say that most of the animation I've shown are from NISA video. I've splitted it into bits, but you've got a very interesting Sentinel-6 video from ESA, where you've got also waveforms and track around the globe and things like that on ESA site, and you can download it in full as you wish, and splitted it into little bits.
I've also just had a note from one of my colleagues, from Ben, who can't be here today, to say that the as well as being able to visit the GitLab to download the code yourself, you can actually also spin it up in things like Binder now. So if you're not familiar with using Python and it's something new to you, you can also just spin it up and try it using that service now as well. But there are full instructions in the READMEs for helping you to install the code if you want to, and the tools if you want to work with it. Okay. Well, if there are no more questions, thank you very much, Vinka and Nick, for your support today, and Regina in the background there. Oh, hang on, is there one more? Please could you explain how the reprocessed data are created? Yes, so not maybe in so much detail. We do provide, every time there is a reprocessing, we issue a product notice, which will tell you what has been done to the data in terms of the reprocessing. It depends a little bit on what's changed as to exactly what the reprocessing will entail, but effectively we will take the whole, usually the whole mission that we have so far, and we will then apply the most current processing version that we have to that entire archive. There may be some other changes that are put in depending on what's changed, if there's issues with calibration and things like that. But yeah, it's usually documented in the product notices that come out along with the reprocessed data sets. This usually happens with a reprocessing if we have a significant change, although actually with Sentinel-6 it's being reprocessed more regularly than maybe you have experienced, say, with Sentinel-3. So if you want more details on that, we can share the specific product notice on the reprocessing with you. Vinko, I don't know if you want to add anything more on altimetry reprocessing in general?
Well, most of the correction or algorithm are decided or discussed during the annual Ocean Surface Topography Science team meetings, and they are often phased with them because they are decided by discussing the best correction during those. You can have a look also at the presentation from this meeting to understand why this one was chosen over that one or things like that.
Okay, thank you very much for that question. And with that, we can close the session. There'll be more short courses coming up soon, so please do keep an eye on the web pages and you can sign up for further ones. And if this is something that's piqued your interest, maybe look at some of our longer courses that you'd be very welcome to apply for and attend. Okay. Thank you very much, everybody, and we'll see you next time. Bye-bye.
Thank you. Bye.
Bye.